for joining us on this webinar for migrating to Micro CPU250 from the RCCs. It's a little longer run time than usual. We're coming in about 25 minutes for the presentation, but as usual, feel free to put in any questions throughout and we'll get to them at the end.
Hello and welcome to today's webinar. Today we will look at migration to the Micro CPU250 from the RCC. Let's take a look at our agenda for today. We are going to start with a quick review of the CPU 250, and then we are going to go through all the different RCC models. We will talk about migration strategies for moving your application over to the RCC to the CPU 250. We will go through all the different conversion steps, and there will be demonstrations throughout, and we will finish with a Q&A session. The new micro modular controller are one of the micro series, which previously only included all-in-one controllers and now includes modular controllers. Now these modular controllers are loaded with capabilities, lots of connectivity options with Ethernet and USB-C for programming and micro SD, lots of built-in I/O for the CPU 250 at least. You can also add additional I/O through standard OCS I/O blocks that you can add on the side of the unit, and all the connectivity with all kinds of different protocols are supported. There are 34 built-in I/O points in total, including 8 of which are flexible between digital and analog. Now let's take a look at the RCC controller lineup. These are a series of models that have been released over the years, starting with the RCC 972 and moving its way through the RCC 6512. So there are currently 5 models in the lineup, although the RCC 2414 has already been obsoleted, but some of you may have an application out there that is using that particular controller, so it is going to be covered in today's presentation. Most of the RCCs have similar features. The micro SD slots are common, at least one Ethernet port, and at least one serial port. Those are all common. DC power input. The voltage range may vary from model to model. They all feature recessed push buttons for starting and stopping the controller or loading a new program. For micro SD, they all have status indicators for run and power, and some of them also have additional indicators for network activity. And then where they really vary for the most part is in their I/O complement, how many digital ins and outs and how many analog ins and outs. They have another area where they vary is also the amount of logic resources available, how much logic space, as well as how many retentive word type registers and retentive and non-retentive bit type registers. So for each model, as we go through them, you are going to see a table in the upper right hand corner that shows those differences. So the RCC 972 is the first one that we have, and one thing that is unique about that particular model is the fact that the RCC 972 does not have a real-time clock or a battery. So that was a requirement for the particular OEM that we designed it for, even though we can sell it to anybody. So that is something to be aware of with that particular model. The next model we have got is the RCC 1410. Some of the big differences here, beyond the I/O complement differences, are the fact that the RCC 1410 has a lot of available registers as well as program space. So it has 50,000% R registers. It has 32,000 bit type registers, half of which are retentive, and it has 2 megabytes of logic space. But keep in mind, the new CPU 250 matches that in terms of all those different parameters. So again, you will be able to see as we go through this presentation today that the CPU 250, part of its specifications were developed so that it could easily replace the RCCs moving forward. From an I/O standpoint, the RCC 1410 has 14 digital in and 10 digital outputs. It does not feature any analog. Now let's take a look at the RCC 8842. It is identical to the 1410. The only difference is the I/O complement. It has 8 digital in and 8 digital out, 4 analog in and 2 analog out. Both the RCC 1410 as well as the 8842 have LED indication on their terminal strips, whereas any RCC model you will see that just has a green terminal strip for the I/O instead of the black ones. Those green terminal strips do not feature LED light pipes, so they do not have LED indications, whereas the black terminal strips do, that are used on the 8842 and the 1410. The next model is the RCC 2414. Now this one is unique. This one is used in quite a few different lighting applications, but is ultimately obsoleted. So if you have got one of these, there is a decent chance it may be used in a lighting application. What makes the 2414 different is the fact that it has 2 Ethernet ports instead of one, and from a serial port standpoint, it has 2 ORs, 485 ports. So that is the two of the things that make it unique. The last thing that makes it unique is it supports for USB. So it has got USB for programming as well as a USB host port for a flash drive. Now, the last model we are going to talk about, and is a very high volume product, but it is primarily used for high speed counting. So if you want a remote high speed counter, this is the product that most of our customers use, and this is an RCC 6512, which has high speed counter capability. It has 12 high speed inputs that can be used for high speed counting, encoders, up counting and down counting, and then it also has some analog built in as well. So it is a very versatile product, but it has a very limited number of resources from a programming standpoint, because it is intended to be a core processor, and due to its incredible high-speed counter capabilities and its limited CPU resources. What are our migration strategies? Well, first of all, most of the models can easily be replaced with a CPU 250, because the CPU 250 has plenty of built-in I/O that can cover any RCC model that exists out there. And even though most of the models have a lot of capacity for programming in terms of programming space and register space, the CPU 250 also matches that as well. So again, that is why moving from most models to the CPU 250 makes sense. Now, in a couple of cases, you may find that you want to transition to a CPU 300 instead. So in a couple of cases, if you need the 2 Ethernet ports, or if you need the high speed counter support as well, plus or minus 10 volt analog outputs, in these cases you might want to transition over from a 2414 or the RCC 6512 to the CPU 300 that we are releasing later this year. But again, even these models in a lot of situations can be replaced nicely with the CPU 250. Now let's talk about what we have to do besides just ordering a different part number to do the migration. Let's start by talking about physical migration. What does that look like? Well, from a physical size standpoint, the RCCs and the CPU 250 are virtually the same size, so they have the same footprint on a redundant rail or in your enclosure. From an I/O wiring and a power wiring standpoint, if you are following the traditional approach of having a field terminal strip inside your enclosure, then you are going to need to rework that wiring from the field terminal strip to the terminal strip on the CPU250, because even though a lot of the signals are the same, the I/O terminals are not in exactly the same location, so you will have to redo that wiring. Now, from a serial port wiring or an Ethernet wiring standpoint, the pin outs have not changed. There may be additional signals on the modular jack, for instance, that handles serial ports, but the signals that were there before for your RCC application are still in the same location for the CPU250. If your communications cables or your Ethernet patch cables or your serial port cables, if they are of sufficient length where you can move them from where they were with the RCC to where they are with the CPU, then no changes have to be made there as well. So that is some of the physical changes. Now let's talk about CAN. There are some big differences with CAN, mainly the fact that even though the CAN wiring was not standardized across all the RCC line, it was always using a terminal strip, whereas with the CPU250, it uses an RJ45 port, which is a modern way of handling CAN. So there are a couple ways of transitioning there. First of all, if you are using traditional CAN wiring and you would like to connect those to some wires to the CPU250's CAN port, well, you can use an RJ45 to terminal strip cable. This is an option that you do have. Or if all you are going to do is, let's say you have got a CAN wiring going to the field terminal strip inside the enclosure, and you want to make that connection to the CPU250, well then from a field terminal strip, you can just run, let's say an Ethernet patch cable chopped off on one end, and then you can connect 3 terminals, the CAN high, CAN low, and the CAN ground to your field terminal strip to the appropriate terminal. Now what about termination? Well, with the RCC, if you are using CAN, then the RCC is on the end of the network. Then almost certainly you have got a physical resistor that is plugged in at the end of the CAN network on the RCC. If it is at the end of the network, you do not have an easy place to put a physical resistor with the CPU250, but the CPU250 does have a software enabled CAN termination, so simply by turning on system bit, you can turn termination on, so you do not have to mess with the physical resistor. So that is another option here. Now this particular slide here shows the pin out that you can use in those 2 scenarios that we went through previously. One scenario is where you chop off that Ethernet patch cable and just wire up 3 pins from your field terminal strip into the CPU250. The other scenario is where you use an RJ45 to terminal strip breakout adapter, like we have got shown on the screen here, and then you can see the pin out that is required in that scenario. The differences in CAN physically are more sufficient than they are in Ethernet and the serial ports. Now let's talk about I/O mapping. From a basic I/O map standpoint, there are not any differences between the RCCs and the new CPU250. Let's go through the differences that do exist. There is a feature that a lot of customers do not always take advantage of, and that is there is a digital input register, %I bit, that will turn on if you have a short circuit on one of your digital inputs, on one of your digital outputs. That is available with every OCS model that is out there. A lot of people do not take advantage of it. Well, in the case of the RCCs, that indication of a short circuit that comes on typically with %I16. Although if you are using one of the RCC 6512 model, then the indication for short circuit is I32, but in either case, in the CPU250, the bit is I25. So if you are using that short circuit indication bit, you will have to remap that one. And then another case where remapping may be required is in the case of analog outputs. If you are using voltage analog outputs, you may have to do a remap of your AQ registers as well, because of the way that works with CPU 250. Now let's go through what you need to do in Cscape step by step when you are going through the migration from RCC to the CPU 250. The first step, as always, you want to archive your existing RCC program and then make a duplicate of that program so that you are starting with a copy of that program. As you make programming changes, then you're going to go to hardware configuration. You're going to change your controller model from the RCC that you are using over to the CPU 250. Then you are going to go into the local I/O tab and you're going to do the configuration that is required, and most of your configuration, and you will see this in the demonstration, is going to be in the flexible input section and the analog output section of the CPU 250, because that is where your analog is required. The RCCs did not have any options for the most part with their digital inputs. For the most part, did not support high-speed counting except for RCC 6512, which is a high-speed counter coprocessor. All the rest of the models did not do any high-speed counting at all, so there is not much configuration that will be required there. It is all going to be on the analog side, and then the remainder of the changes in your logic program are going to be related to your analog outputs, because if you are using any voltage analog outputs, the voltage analog outputs are mapped in a different area with the CPU 250 as compared with the RCC, so you would need to do that remapping for both a register number as well as an I/O names standpoint. And then finally, it is just a matter of saving your program and downloading and testing. For our demonstration, let's do a conversion of an RCC program to the CPU 250. So we start by archiving and then copying our existing RCC program. So let's go ahead and copy and paste that program. We are going to do a quick rename, whatever you want to rename it. And then that is the program we are going to open, which is the one we just created. That was a duplicate. So before we go in and do the conversion, let's explore what the RCC configuration currently looks like. So we will go into hardware config. It is configured for an RCC 8842. Let's go take a look at the local I/O and see how that is configured. So digital inputs, everything is at default with positive logic. Digital output, everything's also at default. Analog input, it looks like we have got two 4 to 20 milliamp channels and two 0 to 10 volt channels with a filter constant of 3 for some digital filtering. On the analog output side, we have got a 4 to 20 milliamp channel, a 0 to 10 volt channel, and we are going to 0 when the controller is stopped. That is the configuration we want to match in our CPU 250. So now back to the hardware configuration, now changing our target to the CPU 250. Now that we have done that, we can go back into local I/O. We can see the picture is different. The defaults for digital inputs, nothing to change here. Still positive logic defaults. For digital outputs, nothing to change here. And now we're going to have to manually make these changes because the analog settings do not follow through automatically. So we have to make those manually. We are going to set our digital filtering to 3 because that is what it was before on the RCC. Our first channel is going to be analog 4 to 20 milliamps with a scaling of 32,000. Our next channel is the same, 4 to 20 milliamps, scaling of 32,000. Our third channel was 0 to 10 volts, again scaling of 32,000. How do we know the scaling was 32,000? Well, that is the only option that you have for the RCCs. They just by default are 0 to 32,000. So now our analog input channels all match what they should. We got our filtering, we have our signal types, and we have our data range. So that is done. Now let's take a look at the analog output side. We had one 4 to 20 milliamp channel, and again 0 to 32,000, because that is all the RCC supports. And when the controller is stopped, we want to be at 0 or minimum. Now we cannot configure the second channel here for voltage, because if you want voltage, you have to go down here to the fifth channel, the fifth through the eighth channel. So 0 to 10 volts, 0 to 32,000, and the hold state of minimum is what we want. But we have to note that our second analog output is no longer AQ2. Our second analog output is now AQ5. So we are going to have to make mapping changes in our program to change AQ2 to AQ5 everywhere in our program. So we will prepare to do that now. So we are done with the hardware configuration. Now we are going to go in and replace every instance of AQ2 in our program with AQ5. Now if we have more than one instance, then the easiest way to do that would be to go to the edit menu and the replace option, and we would do a find AQ2 and replace it with AQ5 and hit replace all. It tells us how many have been replaced. Now if we are using register based programming, we are going to also do a change on our IO name, because we lost our IO name when we made that change. So we need to go over here to IO name, right click, hit edit, find AQ2, which is the old IO name that now needs to be AQ5. Make that change, hit OK, and hit OK again, and now we can see that we have got our IO name along with our proper analog output register. Now if by chance we are using a short circuit indicator, which is either going to be I16 or I32 depending on our RCC model, then we need to change that to I25, so we know that we have only got one instance of this here in our program. So we are going to go ahead and change it from here. But again, if we have multiple instances, we are going to have to change them all manually. Again, we lost our IO name, so we need to go back here to the IO names area, find I16 and change it to I25. Again, we could have done the search and replace technique. That is also valid, but we wanted to show you the other way of doing that by changing it manually here. So now that change has been made, the only other change we might want to make would be if in our RCC we are using a physical CAN termination resistor, and in our CPU250 we are going to use a software enabled termination resistor that is internal to the CPU. So let's put a comment in here. Enable software, enable CAN termination. That is what we are going to be doing with one more quick run. Then we are going to need to put an always on contact here. Again, we are demonstrating register based logic today, and then the SR for software enabled CAN termination is SR152.4. It does not have a default IO name, so we will go ahead and name it now. And there we go. So that is the final change that we need to make to this particular example. Your actual example may be slightly different, but this should give you pretty much what you need to know. Our last steps are going to be to have to save the modified program and then download and test the result. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so we will be, excuse me, we'll be carrying on at the CPU250 next week with I/O configuration using variables. The registration links are up as usual, so if you'd like to register for that, that will be next week's webinar. I don't see any questions on that, but feel free to get in touch if you do have any in the meantime. Okay, I think we can leave it there for today. Thank you all for joining. See you next time.